Emphasis that we now don't have to estimate the closure parameters, the alpha coefficients anymore, but we can actually measure them in simulations and can see how they change when varying supernova rate, rotation rate, and so on and so forth. So yeah, this is work I've been doing with Udo Ziegler, who's been developing the Nirvana code with Detlef Elsen and Günter Rüdiger in Potsdam. And luckily, most of the stuff on interstellar turbulence has already been covered in the lecture that Anwar's been giving on Tuesday, Marit Korpi's lecture. So basically, I can just found everything on that. But I will also introduce mean field concepts again and show how they can be applied to understand the field amplification that we see in the simulations. You already probably have seen that mean field theories are a quite useful concept. There's one thing that I wanted to point you to. This is an airfoil of a plane, and usually they explain you why the plane flies is that the air going over the wing goes a longer way and therefore has to travel faster to meet the air in the rear. And so the air on the top has a lower pressure, which gives you the updraft. Then that's not correct, or at least not entirely correct. It's really important what turbulence is created. And airfoils have been modeled for a long time now, applying large eddy simulations, mean field modeling for the Navier-Stokes equations, and there's been an amazing effort being put into measuring closure parameters for turbulence models. And a colleague told me that he met one of the pioneers of aviation and CFD, and he still thinks it's a miracle that these things fly, because there's so much math going into the concept of mean field theory. So next time you enter a plane, think that what makes this plane fly is actually mean field theory. Okay, so here's the outline. I'll give a brief motivation why we're interested in galactic magnetic fields, then I'll reintroduce really in a nutshell, the mean field concepts, just for introducing my notation more or less. And then I'll give a brief review on what has been done on the galactic dynamo in the last 15 to 20 years maybe. I will introduce then our model of the interstellar medium, which is hugely based on the work that Marit Korpi, Anwar Shukurov, Axel have been doing in the 90s. So that was really very fruitful work, and I could really just take their models. I have so much that I've taken out of Marit Korpi's paper. So I'm really grateful to these. I will talk a bit about the measuring the mean field parameters by the test field method, but we've had an extended talk on that yesterday, so I can probably also be rather brief there, and then I'll introduce you to some of the results I got. So this is a polarization map of a typical spiral galaxy, and you can see these beautiful large-scale structures of polarization vectors which are identified with large-scale magnetic fields. So you wonder, how are these fields created? Are they just a remnant of the formation of the galaxy when the gas collapsed? Or are they really a dynamic process? Do you need to recreate them permanently to sustain them? And one argument in favor of this is that galaxies are known to be turbulent. From spectral lines, you know they are thermally, and they are broadened wider than they would be thermally broadened. So you have to assume that there's a turbulent velocity field, and you can measure that they have a 10 kilometers per second turbulent velocity on average. So you can do the math and calculate for a field of this scale, calculate the diffusion time, and this is a couple of 100 million years. So you would expect that any field stemming from the creation of the galaxy has long decayed by the time you observe it. And these fields are strong. They are in equipartition with the gas pressure. Another argument in favor of dynamo theory is that these disks, they rotate differentially due to the gravitational force of the central dark matter halo. So you would basically, if you start with a field that threads the disk with any field, that's actually a nice illustration in a book on cosmology where they take the picture of a cow and then shear it out by differential rotation. So you can take everything, it will look like spiral arms in the end. So if you start with a galaxy that's threaded by a uniform field, after some time it will be sheared out, and in the end you always get these spiral patterns. But what you see here is that if you take a radial direction and then look at any of these vectors, they have an inclination towards the azimuthal direction. So you have a quite large pitch angle, that is called. So you have a strong radial field. And radial field you cannot explain by differential rotation. So you need a mechanism that creates a radial field, and this is exactly the alpha effect. So these large pitch angles really make it necessary to have a dynamo mechanism. So I think we've seen the Sombrero Galaxy before in your talk. So I find it a really nice picture. You see that it's really turbulent here with the occultation of the... so you have this extremely turbulent interstellar medium. You have energy deposited by various sources. You have the dominant, of course, are supernovae, as we heard. They can deposit as much as 10 to 51 Earth, or the equivalent of 10 to 40 nuclear bombs. You have cosmic rays. You have the magnetorotational instability that Anwar has really nicely introduced us to. You have contributions from stellar winds and protostellar jets as well. But here we want to focus on the supernovae. And in our own Milky Way, that's 2 or 3 per century, which might not seem a lot, but if you think in terms that you follow the evolution on a giga-year time scale, that's really several thousands of explosions. And we'll see that in one of the simulations later. So how do you actually amplify fields in a turbulent environment? And we all know that this is rather simple. As soon as you have rotation giving you Coriolis forces, you can create vorticity. And if on top of that you have some inhomogeneity, like stratification, from this vorticity you can create helicity. And if you plug that into the induction equation, that gives you a source term. So you would think it's actually rather straightforward to get a turbulent dynamo in a disk galaxy. The problem, as it turned out, and what was a major obstacle for quite a while, is that you have a disk wind, and really it wasn't quite clear what the turbulent transport would do. So there were different scenarios. Some people said, yeah, the wind just blows away the fields before you can amplify them. Other people said, no, there's a strong downward pumping. And then yet other people said, okay, the downward pumping will lead to the field being compressed to a narrow region in the midplane. And if you compress your field, you get large gradients, and that makes it very vulnerable to dissipation because you have turbulence there. So both scenarios would inhibit dynamo action. And actually in the simulations, in the end, we'll see that these two processes, the wind that drives out the fields and the turbulent transport that pumps them to the midplane, they just balance. So there seems to be some energy equipartition that really puts it in a place where we have a dynamo action. So what people have been doing to explain these large-scale coherent fields was they applied large eddy simulation. That's mean field models where you cannot resolve the turbulence scales, but you parameterize your underlying turbulence. And these were actually quite successful in predicting the field topology and the amplification. Usually it was the amplification times were a bit too low, and so the main problem of these was how do you get your dynamo parameters. I mean, you can always do back of the envelope, you can estimate the turbulence velocity, you can apply Soka theory, and that more or less worked out, but as we see, there's some issues about predictive power there, and I'll come back to that. So, introducing the mean field approach, we've seen this several hundred times probably already at the school. So, just for notation, I still use the dashes. It's a bit old-fashioned. So, the program basically is split your quantities, derive the mean field equation, and then obtain some sort of closure. And try. In classical mean field theories, these closure models were usually gauged against empirical data, so they were really doing wind tunnel experiments and all that sort of thing, and to fix the free parameters. But we can't really, we're not in this position to do that for astrophysical applications. So here's how we derive the mean induction equation. So this is just a normal induction equation where I have splitted the fields. You can see here there's 4 terms emerging from this induction term. And now these averages have to fulfill the Reynolds rule. So that means that you take averages of averages, doesn't change anything, and the fluctuations have to vanish. And from that you can derive the rule for this mixed product. That basically works that this mean here isn't affected by taking other mean, applying this rule. So you can pull it out of the product. And then you use this rule to show that the mixed terms actually vanish. That doesn't work, for example, for the term where you have 2 fluctuations, because the fluctuation you cannot pull out of the average. So it's really crucial that you use these 2 on the mixed terms, where you have the mean and the fluctuation, and the fluctuation in the mean. So 2 of these 4 terms cancel here, and you arrive with this mean field induction equation, which formally looks like a regular induction equation, but has this extra term, the turbulent electromotive force, which is the correlations of velocity fluctuations and magnetic field fluctuations. And that's all subsuming the effect of turbulence. So how do you get a closure for this? So the aim is to find an evolution equation for the mean EMF that only depends on a parameterization for the mean EMF that only depends on the mean quantities. You want to get rid of the fluctuations, obviously. So what you can do is write an evolution equation for the mean EMF that assumes that the velocity field is given, and you need an evolution equation then for your fluctuations in the field. So what you can do is take the full induction equation, subtract the mean induction equation, and what you get is the induction equation for the fluctuations. And as always, when you do that for turbulent closure models, you run in that problem that this equation now has triple moments if you put it back in here. So you have 1 dash here and 2 dash quantities here. So you have a term that depends on 3 dash quantities. And if you now, you can get a cascade of equations, but that's usually not what you want to do. So a simple closure is just to neglect these terms, and that's what is called the SOCA, or second order correlation approximation. And then you get this equation, and in the limit of eta going to 0 for high Reynolds numbers, you can neglect this term. And then you can derive a term that shows you that your induction term is proportional to the kineticalicity. Probably boring you at this point already, so let's go through this a bit quicker. There's a, as I find, quite important paper by Leonid and Günther from '93. They derive analytically in the framework of SOCA the alpha effect as a function or in a stratified medium. So you see on the right-hand side you have gradients of the velocity, turbulent velocity, and gradients of the density. And as always in the SOCA, you have this free parameter here, which is the correlation time of the turbulence. And these also depend on the rotation rate, and these psi functions, these are quenching functions. So this is something that starts off at 1 and then goes down. In this case, these are rotational quenching functions, so they depend on the Coriolis number, which is simply your correlation time versus your rotation rate. So this tells you how fast are you rotating compared to the coherence time of the turbulence. But these are in the case of the galaxy, are rather close to unity, so we don't have to worry about them too much.
I think in that paper they actually had a u squared, or a factor 2 in front of the logarithm, whereas in the original paper by Krause and Karl-Heinz and Steenbeck, they actually had exactly this formula. So I think this is an open question, perhaps. How exactly is the relative importance of rho stratification versus U stratification? And should be checked numerically, I think.
Could be, yes. And I think there's also a different way to write this if you pull this into
Sure,
this.
Exactly, yes. Yes, it's also not confirmed.
They should, well, physically, they should combine into something like, to some approximation, to rho U squared, because what is important is the pressure scale height, right?
That's what Goethe had, yeah. And Leonid.
The pumping term, the gamma z, I will introduce that shortly. This depends on the product of rho and u dash. So,
You're sure there was a rho? But then again, it's also not it's fully confirmed, I would think. Yeah, by the way, is there not a minus sign in the gamma formula? Down the gradient always. Depends how you write, by the way.
Oh yeah, I think I have a definition of a minus in that.
I see.
So positive gamma would be downward pumping. Is it? I would have to check. I actually found that these reproduce the profiles that I get from the simulations quite well. So we'll see that later. So this is basically what you can do with quasi-linear theory, but we still have these u dash and the rho as input parameters, and it's quite difficult to estimate these from observations, as we will see. So just to introduce the alphas and the etas, we want to, as I said, parameterize the turbulent EMF, and so we introduce this alpha tensor, which relates the vector of the EMF to the vector of the mean magnetic field. And then we have this rank 3 tensor that relates it to gradients in the magnetic field. And as we've already seen, one can simplify this to a rank 2 tensor, assuming only a vertical dependence. So I will always assume that I'm using a 1D mean field model now that only considers the vertical coordinate. And so I call this eta tilde. And now we want to determine these parameters, either applying some analytic formalism, or we can measure them from the DNS. So how can we interpret these? In this simple case, I've written the tensors in coefficients here. So the diagonal elements of the alpha tensor give you the dynamo effect. They basically create a feedback loop. If you go back to the induction equation, you have the curl E there. So the curl means you swap these two, and the matrix also swaps them. So you can see, if you, that's the next slide, you can get a feedback loop, and that's what basically allows you to amplify fields exponentially. Then the off-diagonal elements, there's a main contribution from the totally antisymmetric tensor here. So because I'm only concerned with the vertical direction, the gamma y and gamma x are 0 in my case, and these two are assumed to be antisymmetric. And that's a good approximation for the galactic case, where the rotation and the gravity are aligned in the small box case.
Is the gamma here defined upwards, yeah?
Yes, that doesn't seem to be consistent with it. Yeah, maybe I just took the formula from their paper and they had it the other way around. So the eta tensor, the diagonal elements are just the what is known as turbulent diffusivity. So they should all be positive. That's a check for our measurement. And then there's also the antisymmetric off-diagonal part, which also has the Z contributions here in my case only. And this is the so-called omega cross J effect that Karl-Heinz Wedler discovered in the 60s. And there's actually some relevance to this in my simulations. So it was long discussed whether this has the proper sign to give a dynamo, and in here it's actually together with the shear you can amplify fields with that. So if you plug this parameterization back into the induction equation, you get a system of partial differential equations describing the evolution of the mean fields, and you can see that the evolution of the radial field is coupled to the evolution of the azimuthal field via this alpha phi, and that the gamma z shows up at the same place as the velocity. That's why we interpret it as a turbulent pumping term. So this, it's not an advection, it's really a turbulent effect. It's like diffusion, although it's not in the sense like diffusion that it destroys gradients. It's just in the sense of being a turbulent effect rather than a mean flow. And here's the turbulent diffusivities that add up with the molecular ones to give the total diffusivities. And here we see that this delta z term now couples the gradients in d phi to the evolution of BR. So there's also a means to get a feedback loop. And in the phi equation, because we have differential rotation, we also have this shear term, which is usually thought to be dominant over the alpha r term. So we don't really need this guy here. And then you can define the dynamo numbers, as you've probably seen plenty of times here already, where you relate the induction effect of the alpha to the diffusivity with some characteristic length scale to get the units right, and the induction effect of the shear. And depending on how large these numbers are, you have different dynamo regimes. So if this is 0, if there's no shear, you usually speak of omega square dynamo, alpha square dynamo, because you need both the alpha r and the alpha phi to close the loop actually. In the case where there's an omega, you can dispense with the alpha r, and then you have an alpha omega dynamo. And in this case, you need the product of these two numbers to tell you whether your dynamo is supercritical. And there's also an interesting thing, the pitch angle in the kinematic phase, so if you're not saturated yet, can be approximated by the ratio of these two numbers. So you need a strong alpha effect to actually create a non-vanishing pitch angle. And if you then do 1D mean field simulations with these equations, you can get these nice traveling wave patterns, which are, can be, if you describe this, the thing is, as soon as your dynamo parameters are functions of space, it's not, you cannot really linearize it anymore. And but you can show that there's, in the simplest case, that there's an imaginary part to it. So you get actually traveling wave solutions and oscillating behavior depending on the ratio of the coefficients, of course. There's two examples for differential rotation. We have a positive alpha, which leads to patterns traveling towards the midplane. And in the case of Cartesian shear, we have a negative alpha, which leads to waves traveling away from the midplane. And as we'll see, that's crucial in determining the growth rates, because if you have a wind going away in the pumping, that can drastically change the oscillating behavior of the dynamo and the parity and also the growth rates. And
so usually you don't get dynamo waves in the field as alpha omega dynamo. So why do you get? Is it because of the gamma term?
Yes, exactly. It's really, if you set the gamma to 0, you get a stationary solution, and only if you have the gamma on the order of the alpha, then you get the traveling wave solutions.
And what about the boundary condition outside?
They also play a role. You can actually turn it around if you have the insulating versus pseudo-vacuum boundary conditions. So they also play a role in determining the...
So if you take pseudo-vacuum, you get these oscillating things? Or?
I haven't tried this recent paper you had with... you showed that if you can get both in both cases, right?
Yeah. Now, in your case, first of all, you have antisymmetric solutions.
Yes.
Which is also normally expected to be differently for the galaxy.
mean, the fastest growing one is a symmetric quadrupole thing normally, but something has changed here.
It changed considerably, and there was a paper by Brigitte von Rikowski, and she looked into this, and it really changes the picture dramatically when you have a vertical advection velocity and pumping.
So is your boundary condition more like perfect conductor? Because then you would
These
maybe.
are setting, you can see it here, I'm setting the fields to 0 here.
So that means pseudo vacuum then.
Exactly, yeah.
Mm.
Okay, but this was basically just to show what you can do with these mean field models. So I want to give a brief review now on what has been done in application to galactic dynamos. So as I said, if you take quasi-linear theory, you can in principle use the SOCA framework to derive your alpha and eta out of a density profile and a turbulent velocity profile. And you have to now assume hydrostatic equilibrium to solve your momentum equation in the vertical direction. So you cannot consider a wind. And this has been done by Sokolov and Shukurov in a Nature paper in the 90s, and later by Hans Ehrlich and Manfred in Potsdam, who derived these profiles of the alpha terms as function of the radius and the vertical height. So from these you can, in principle, get order of magnitude amplitude of your effect and the proper sign. There was some discussion, however, about the sign of the alpha set, which does not enter my formalism here. I should have mentioned that because this doesn't have any relevance if you only consider BR and B phi, because the B set in my local approximation is constant. But there has been some uncertainty with this method. Plus, you cannot consider the mean flow. And the simulations clearly show that there is a mean flow of the order of 10 to 20 kilometers per second. So it's non-negligible. Based on these estimates and applying basically the formula of Kichatino-Rüdiger 93, there have been mean field dynamo models. There was a paper by Axel and a number of collaborators who were concerned with the halo dynamo and also looked in the effect of winds and pumping. And there's been 2 papers by Rode, Beck and Elsner, end of 90s, and they tried to explain the strong interarm fields. If you look at these polarization maps, you will find in a couple of cases that the fields are actually stronger in between the spiral arms, so the density is low. And wanting to explain that, they assumed that the turbulence velocity field, which is an input parameter to these dynamo models, of course, will rise with the spiral arms. So this on the left-hand side. So they assumed a spiral arm pattern. I probably can't read this here. And if you then tweak your coherence time, this is also a major unknown. People assumed something like 10 million years, 20 million years. If it didn't give you a dynamo, then went to 50 million years or 100 million years, and then you got a dynamo, obviously, if you just turn the knob and make the alpha high enough, then at some point you obviously get a dynamo. So there's a bit of a issue with this coherence time there. So what they found is strong interarm fields as expected. Then a couple years later there were new observations that found wait, the turbulence velocity doesn't vary with interarms. So they said, all right, then let's just assume the coherence time is different in the arms and interarms. And again, they found nice, strong interarm fields now based on the assumption that the turbulent turnover time will rise with the spiral pattern, for which there is little to no observational evidence. So what I want to point out, the predictive power of these mean field models is really strongly related to, so there's fucking one is strongly related to how you obtain your input parameters. And so there's really a need to obtain these alpha and eta parameters based on first principles.
Or, for example, this what worried me here. This correlation time is totally unobservable thing. So in such cases, I think it's better to adopt some model to express unobservable things in terms of observables, and then you will be perhaps a little bit better off.
There's there's a lot of uncertainty there, so that's really why people already quite early at the beginning of the 90s, the models of Katja Ferrier, they try to really base it on hard physics. Like we've seen that the cooling function based on molecular physics predicts you the turbulent velocity dispersion, the ISM.
But the correlation lengths can be observed, I guess.
This is what I say. Better to say that tau correlation is equal to L over V.
Sure.
At least you know what you are doing. Well, make this. Then both will be observables.
So, yes, you still have to make assumptions then. And so people try to really base it on a solid foundation. And as I pointed out before, the main energy input in the interstellar medium is from supernova explosions. So what people did is look at supernova remnants. This is a picture from the simulations already. So this is a simulation box, and these are supernova remnants. This is at a very early phase, so you can still identify them. And what's color-coded here is the radial velocity. And I sort of managed to reproduce a Pepsi logo here. So what you can see here, these are 3 slices at different vertical position set. So you can see that this remnant, where we cut through here, is differentially twisted. So near the equator, the Coriolis forces have twisted it quite a bit already, while near its south pole, it's only twisted a bit. And this is exactly what you need to create an alpha effect. You have a remnant expanding in all directions. So it's expanding here in the mid-plane, so the Coriolis force will give it a twist. Because you're in the rotating frame here. And as you know, the Coriolis force depends on the velocity. So here, the radial velocity is larger than it is here. So the twist introduced here is larger than it's here. And now, on the northern hemisphere of this thing, you also have an upward motion, of course, because the thing is expanding as a whole. So you get some twist here, which is correlated with the upward motion, and in the lower part equally. The twist is the same, of course, but the vertical velocity is opposite. So you get if you plot this in terms of an alpha effect.
How did you know there was a duster inside that cupboard? Sorry.
I think I've seen Axel yesterday. So you get a positive alpha effect here and a negative alpha effect here. And you can estimate the shell velocity of the thing. So you can estimate that this is in orders of kilometers per second, just as you need it. I think I have a movie here.
But if it's completely symmetric, they cancel?
Exactly, that's the point that will come to in a second. So here I just move the slice up, and you see how these remnants are twisted differentially. And so that's really nice picture book approach to cyclonic effect that Parker predicted for convective bubbles in the sun.
But Oliver, I think that in the Milky Way, this contribution of this twisting of the expanding shells themselves contributes at most 10% to the helicity, total helicity, which is mainly in the interstellar turbulence, in the motion of the diffuse gas.
That's true. I mean, if we see the simulations, it's fully turbulent, so this nice picture of the expanding bubbles doesn't really hold, but that's really the basic assumption that went into the calculations of Katja Ferrier, that really it's an uncorrelated ensemble, how she called it, that you have single remnants and you can just superimpose the.
But still, even then, the value of alpha she obtained was factor of 10 smaller than you get from turbulence in the diffuse gas, driven by the same supernova.
The problem was if you take this profile of a single remnant, you now have to do the convolution with the supernova distribution. If you assume you have a supernova distribution psi of z that has a certain scale height, or let's start with an even more simple thing. Let's assume you have a constant distribution. Then you have a remnant here. Then you have a remnant here that gives the same effect. Then you see these two guys, they cancel out. So if you do this and assume a constant distribution of remnants that overlap, then each contribution from the neighboring ones will cancel out, and you have basically a vanishing effect. And even if you assume a supernova distribution that is Gaussian with a scale height of something like 90 parsecs, as is observed, which is the thickness of the dense disk, you get a lot of cancellation if you do the convolution of this with this. So you have to think of this sliding along here and doing the integral, the convolution integral of your alpha of z minus z dash psi of z dz. That's what's called the approximation of the uncorrelated ensemble, that you can compute the effect of just an expanding bubble and do the convolution with the distribution here. But the wider this distribution gets, the more the amplitude of this actual effect is attenuated. So you actually need to assume a delta peak to get a reasonable amplitude. So that was the problem that the early models of Katja-Ferrier had.
Not just because there's no horizontal distribution as well. I mean, they'll only cancel out if they're actually in line. If you then distribute them horizontally, then they don't cancel each other.
Exactly. So that's another caveat that you. The way that Katja-Ferrier went with a follow-up publication was she said, okay, let's now look at superbubbles, correlated explosions, and there you get a higher coherence time, and then your alpha effect gets stronger, and then.
That's still 10%. Of what comes from diffuse turbulence.
The main problem with it was that it does not only predict the diagonal alpha, but it also predicts the turbulent pumping, the gamma term. And it found that if you do this, you get a gamma that's dominating by a factor of 50. And so this makes dynamo action highly unlikely. But there is actually... So I was already talking about these early models of Katja-Ferrier where she derived the EMF for such a single explosion, which is really a nasty bit of work. And there's also been semi-analytic work by Kaisik et al. In '93 and later by Udo Ziegler. Actually, Udo developed his code to do this project, so that was his PhD thesis in '95 as a side. Where they would do simulations of a single bubble. So you would do 2D and 3D simulations of such a bubble and then measure the alpha by imposed field method. And that was, he found very similar results in the analytic work of Ferrier. So that was okay, but the problem is when you do the convolution with the distribution here, then you basically, you smear out your effect and you have a lot of cancellation. The solution to this is actually, and that's been done by in the paper in end of '90s, to consider a stratified ISM. So if you have actually, these all assumed a constant background pressure, constant background density, so these things are nicely spherical. But if you now have a stratification, the pressure falls off pretty quickly. So what that means that you have a lower external pressure, and if the thing goes off slightly away from the midplane, you get these pear-like or peanut-shaped bubbles, because the pressure here is much lower, the thing expands faster here, and it expands slower here. And this is leading to a now or skew profile. So here you have a, maybe I'll use color. So this would lead to, as you can see from the shape here pretty clearly, that leads to a large contribution here and a low contribution here. And if you now consider that you have something that is more symmetric around the midplane, and then a guy that is exactly opposite on the other side, then you can see, if you now do the convolution of these, so you have the white guy here, and it becomes gradually more symmetric here, and then you again have something that's skewed in the other direction. You can see that you now get a net contribution if you do the convolution, because this will not exactly cancel out with the smaller contribution here anymore, so you in total get a positive contribution here. So this stratification really increased the amplitude of the effect that you get by quite a bit, and now the alphas were actually on the order of kilometers. So the stratified model, considering the uncorrelated ensemble, is actually not as unreasonable as I first thought, but the main problem with this is that it still predicts a dominant pumping, and also it predicts a positive pumping. So if you do this, this will tell you you blow your field out of the disk by turbulent pumping at a factor of 10 faster than you create the field, and this gives you dynamo numbers that are subcritical. So the bottom line of these works in the 90s was the galactic dynamo will never work by supernova explosions because they are too violent to, they are basically destroying the field faster than they are creating it. So this led to a bit of a crisis in this field, and people were searching for alternatives.
Because before these papers of Katja, nobody even thought about attributing their dynamo action to expanding shells. It just, she asked the question, the answer was no. Let's continue with the old idea. The old idea was that turbulence in diffuse medium drives everything. And it has no problems whatsoever of this type. Okay. It was just a wrong path which you have followed. It ends. Go back.
Okay, good. Because if you read the recent review of Kulsrud and Zweidel, they quote like 10 papers of Katja per year.
Don't read it. Just don't read it straight.
Yeah, that's what I thought. They only cite one paper by the Potsdam group, which is the Steenberg-Krause.
Another reason not to read it.
Yeah, so actually the SOCA prediction for the ratio of the alpha to the gamma is 2. So they say the pumping is 2 times stronger than the alpha, which is okay, and which is actually what I find in the simulation. So it's really a turbulent effect, and all this bubble thing was a sort of a red herring or a sidetrack. But people were rather pessimistic about whether supernova-driven turbulence could actually do the job, and so there was this idea by Parker also that you need cosmic ray bubbles, but it's also not quite clear whether that would work. So what has been done simulation-wise to try and obtain a closure? There's kinematic simulations by Brandenburg, Noss, Shukurov, and then there's been MHD simulations. Axel has computed the alpha effect from MRI, and that gives you a negative contribution, so that but we've heard that MRI is probably not really relevant for the galactic case because the supernova turbulence really dominates. And there's a new paper by Marit Korpi, which just appeared on AstroPH, where she actually looks into at what background turbulence level, can MRI still work or not? There has been simulations by the groups of Misha Hanash and Katashina on cosmic ray driven Parker instability, so that we've seen that in Anders' talk, if you have cosmic ray bubbles, they can lead to buoyancy, and that works, but you need to assume rather high diffusivities for the cosmic rays, and that's not backed up by observation, so it's not quite clear if that's really relevant. And there's been the question whether that's really a fast dynamo, because it seems to rely critically on including explicit dissipation. And then there's been simulations of supernova-driven turbulence for quite a while now, and there's models by the Breitschwert, which have tremendous resolution. I had tears in my eyes when I seen the first animations. They have 10 kiloparsec boxes at resolution of effectively 1,000 cubed, and they really put a large effort in it. And there's also been hydro simulations by John McClough, but these simulations, they relied on mesh refinement, so they didn't include the shear that we need to get a dynamo. So all these simulations are lacking one or more ingredients that you really need to get a working dynamo. So either the kinetic feedback or the shear. So that's basically a starting point of my PhD thesis now. We wanted to develop a model based on first principles. So all the input physics is known and on a solid foundation. And from that we wanted to derive the dynamo parameters. And so here's a typical simulation box. They are quite elongated in the vertical direction. So we're local in the radial, and we're interested in the vertical structure, so we elongate it. This is 800 parsecs on edge typically. We assume shear periodicity in XY. I'll show you how that works in a second. A physical ingredients is non-ideal MHD, so we wanted to be at an explicit magnetic Prandtl number, although it's not 10 to the 9 as in the galaxy, but 2.5. So basically, we are on the right side of the 1. So the interstellar medium is characterized by very high magnetic Prandtl numbers, and so we're trying to go in that direction, but it's really hard. So 2.5 is the most I could really achieve. We need radiative cooling, heating, as Anwar has discussed it, also including the thermal instability to balance just the energy input from the supernova. If you just drive turbulence by injecting thermal energy, that system will run away thermally, so you need to balance that. And really, this is really, I don't like this phrase standing on the shoulder of giants, but this is really largely based on the work that Marit Korpi has done with Axel and Anwar and Orchid in the 90s. And they were really ahead of their time, so they didn't have the computing power to really get it there. But my model is really largely based on this one, so this is really where credits are due. So a bit about the code I'm using. That's the Nirvana code that Udo Ziegler has developed, as I said, for his PhD thesis, who did single supernova remnants. It's now a different scheme, so the first code was based on SUS, but this is like a complete new engine. This is a finite volume Godunov code. So I'm not sure if you heard anything about finite volume codes. It's the idea is basically to consider a Riemann problem at the interfaces and use that to estimate fluxes, and then you can fulfill the divergence theorem to machine accuracy and conserve all your quantities. That's also important that it's a conservative code, which means that it evolves the total energy. That means all your dissipation gets into thermal energy. And as soon as you want to do physics based on the real temperature, where you need the temperature as an input to the cooling function, it's really crucial that you have a conservative scheme to get it properly. The code also supports adaptive mesh refinement, as you can see here. That was an ANA cover, actually. That is a protostellar core collapse. And Udo could show that if you include magnetic fields, you actually get a fragmentation into a binary system rather than a monolithic collapse onto a single star. And the code is now efficiently NPI parallel, and it's available on this website here. you can get your own copy. And the latest thing is it's now also available in cylindrical and spherical coordinates. Udo already did a proof of concept simulation, a convection in a spherical shell, and he also did quite a good job on regularizing the coordinate singularities. Why does it reload the page if I use the laser pointer? That's weird. So he actually can simulate it right to the pole. And there's some sample applications that have been done with the code. Here's a...
So there's no periodic boundary. What are the boundary conditions?
I'm not quite sure. So this is really a very new development. So we're still in the state of testing this.
So this sphere in a sphere, not a sphere in a box.
No, that's a sphere in spherical coordinates. And it's been quite an effort to formalize the finite volume scheme in spherical coordinates, because you have to you do the flux integrals on the surfaces, and if you have now a curved surface, you have to make sure that your collocation points are in the right positions to get the approximation to the flux integral really to second order. So that's I don't think that's actually done before to do a finite volume code in. Yeah, that's the AIP cloud shock cloud collision. Okay, so this is have a look at the code. You might find it useful, and we are always happy to give basic support to get you started on the code. So just send me or Udo Ziegler a mail.
Can you say a few words about the regularization near the poles?
Actually not, no. I've only been chatting with Udo about it, so I don't know how it's done. But, it's not quite 100% perfect, but he managed to remove a lot of the irregularities that you usually have.
For the AMR part, did you observe any spurious reflection at the interface of different spaces?
No, there's synchronization steps that make sure that you match the flux integrals, and you can actually the AMR doesn't work for curvilinear, so this is only in Cartesian geometry, but there's care taken to synchronize the fluxes, and in the finite volume scheme that's really to machine accuracy, then that you don't get artifacts at the separate interfaces. A bit about constraint transport. That's what you get if you do a Google image search on constraint transport. What I actually wanted to get was this. That's sort of one of Udo's papers. So this is a grid cell, and as I mentioned, we use a finite volume scheme, so we compute the fluxes across the surfaces, and in an analogous fashion, you can now, just as you discretize your Gaussian identity over the volume, you can now do the Stokes theorem over a surface, and then you basically compute the electromotive forces along these edges, and then you can show that you can conserve your divergence B constraint to machine accuracy just by construction. So that's in numerical MHD, that's always a problem. Okay, let's move on. These are the equations. That's the left-hand part is just a standard MHD with a total pressure here, and that's the mass conservation, energy conservation, total energy here, the E, momentum conservation induction equation. And now we move into the local Hill system, which means we get additional source terms on the right-hand side. And this is, of course, because we're in the rotating system, that's the Coriolis force. Then we get, from the local expansion of the equations of motion, we get a tidal force. This is just because your rotation profile depends linearly. So if you have a disc and you put a box here, the disc rotates differentially, so it rotates faster to the inside. And if you now take the approximation of a shearing sheet here, that will give you a velocity profile that has to first order a linear contribution. So this is what's called the shearing box, and that's what you need to properly model the sheared system locally. We have vertical gravity, and then we have the energy input from supernovae. This is a picture of the shearing box. You need.
There are no explicit resistive.
I didn't put them here because it would have blown up, but they are implemented in the code. So you need to do some interpolation because this shift can be a non-integer number of your grid cell. So this is not straightforward, but it's doable. This is the concept of a shearing box. So you have your computational domain, and your neighboring domains now have a certain offset to you. That's just to model the shearing dynamics. And the first time I really understood how a shearing box works is when I found this nice vortex here traveling. You see it moves upwards to the left pretty quick, and at the same time it moves downwards at the right and comes into the box again. So this is really what the shearing box does.
There was an epicyclic motion, right? Or the block
yes,
itself?
no, yeah, it goes back. You don't see that in this. You can see that it slows down and it goes back. So it basically moves in a circle. But the circle in this case was larger than the box size.
Yeah.
So we've already seen this in Anwar's talk. We have a volumetric cooling function that goes with rho squared. We have the UV heating function that goes with rho, and then we have the discretized energy input here. We also clustered the type 2 SNE, and we've seen that we see that this makes a morphologic difference to the turbulence. So it's quite there's a lot of details, but in the end, it's quite a reasonable approach to turbulent ISM. We have the thermal instability. So if you look at the logarithm of the cooling function versus temperature, we see that it has a steep dependence here. And if you look at it in a phase space diagram, that's P versus rho, you see that there's a negative slope here, and this is where the thermal instability kicks in, as Anwar has really nicely explained.
To what extent is the cooling function physical, and to what extent is it adapted from numerical?
It's really cruel. You see that these different curves that I plotted from the literature, sometimes they vary by 1 order of magnitude, so it's really a rough estimate. What we had to do to make it work is make it continuous. This original ones by Sanchez-Salcedo, which we used for so we basically combined 2 of them to get a cover of the whole temperature range. But we needed to make them continuous because we were running into, as you mentioned, numerical problems if they weren't continuous. So quick run through on the thermal instability. You get the slope here, and depending on whether you want an isobaric, isochoric, or adiabatic instability, you have these criteria. You see, you get the isobaric already, the slope is smaller than 1, which in the P rho diagram would correspond to a horizontal line. This leads into a segregation into cold and warm ISM, as we see here. That's a mesh-refined simulation of a condensation here. You see this is the small bit here. That's 8 refinement levels. Miguel de Aviles is always very keen on mentioning that the old idea of this pressure equilibrium by Field and by Ostreicher doesn't really hold, because you're really in a turbulent regime and you have a rigorous mixing. We see that in a moment. We see that here, if you look at the phase space diagram, you see here this is the cooling curve, this is the unstable part, and you have material move. This is a histogram of the volume fraction. The color coding gives you the fraction of the gas in the state. So you have the gas moving away to the stable branch here in the cold phase, and the stable branch in the warm phase, but you also have a considerable amount of material in between in the unstable phase. You see here the density histogram, you see a double peak structure with the cold and the warm phase, and you see that this is a rather broad distribution of pressure. A pressure equilibrium would be characterized by a delta peak here.
But still narrower than the density distribution. Right?
Yeah.
Everything is relative.
In a sense. Here I have a movie showing the onset of the instability. This is actually for the parameter set that Axel and Marit used in their simulations to show that you cannot drive a turbulence by TI alone. And you see these interfaces forming that you can nicely follow with the mesh refinement here. And I figured that taking the field length as a refinement criterion similar to the Jeans length in the gravitational collapse is a nice way to follow these interfaces, and that you can save computer power rather than if you just use a standard criterion for your mesh refinement.
Why do they become elongated? Is that a field lines there?
What's that?
Picture?
That's
shear,
random motion, and there's some surface tension, I think. It's really like
in that picture there was the magnetic field also?
I think you had shear, maybe. Did you have shear in the previous movie?
No, in that one not.
No?
So this is now viewed from this side. So this is the vertical direction here. And what you can see nicely here is the radial motions that the MRI drives. So here we have a strong vertical, a weak vertical field that drives MRI, magnetorotational turbulence. And you see if it sets in, it drives these strong channels. And here it leads to the continuous formation of these cold clumps. It's something I've been looking into with Rob Piontech.
Sorry, where is all these things which are describing? It's too fast. What did you show?
I'm running late. I really think I should go ahead and this is a convergence study we did on a single explosion. So this is something like this, and we followed the shell position as a function of time, and there's a nice analytic result by Chioffi et al. And this shows you the relative error as a function of grid resolution, and the line here indicates first order conversion. So it's converging slowly, but it's a reasonable assumption. So it's really hard to model these things, and we have to model thousands of them. So this is really a reasonable approximation to the thing, although it's not perfect from a numerical viewpoint.
How big was your injection site for the supernova?
I used a Gaussian kernel of a few 10 parsec and spread it out over Gaussian. And that worked quite well. I mean, this
seems to be the best choice, right?
Yes. John McLeod, they cleared up a spherical volume and equalized the density, but I don't found that this is really necessary. I think I'll skip over the test field method since we've seen this very very extensively yesterday, Matthias Reinhardt, and I come to the results section. This is not a cosmological simulation. It perfectly looks like one. You have the voids, you have the sheets, you have the filaments, and you have the cores. So it's kind of funny because this is just a natural way to look at structures, right? You have 3 dimensions available, so you have 4 different dimensionalities, or objects of different dimensionalities. So this is really a patch 200 parsec of ISM structures by supernova explosions. So these are not voids in a sense; they are bubbles. They are blown by supernova explosions. I also have a movie for this one. So this was a 200 parsec cube. This was to do the high resolution and the nice movie. So here you can see how vigorous the driving really is from these explosions. You really can see them. This is the density, pressure, temperature, and the magnetic field amplitude. And you can see the cold phase forming here. The dense small clouds, and you have the hot area that really gets heated up to 10 to 7, 10 to 8 Kelvin here. you have a range of 6 orders of magnitude in the density, you have a range of almost 6 orders of magnitude in temperature, so these are really demanding simulations, so this is really a benchmark for your code. If you can do that, you can probably do almost everything else. When it comes to the start, the next time watch here, you can see also the twist, the twirl of one of these. And what you can also see is that you have a small scale dynamo. You get the magnetic field condensed in these. See, here was a swirl. Condensed. And if you look at these two panels, you actually see a nice correlation. The magnetic field is strongest in regions of high density. So, and that if you plot the scatter plot, you get a slope of 2/3, which would mean that you compress your.
But there is no spherical symmetry. Compression in shock waves is linear, right? One dimensional. So you should expect B proportional to rho instead.
So
compression in shocks gives you rho.
Yeah, but you see that these are clumps rather than shock fronts, right? So it's really a 3-dimensional compression. Or that picture where if you compress your volume, you can compress it in 2 directions, and in 1 direction it's not. So that's what gives you the 2/3.
Then it's an illusion, right? That we have magnetic filaments. If there are filaments, it must be raw. It must be 1-dimensional.
Yes, or it should be.
It can be the thermal stability favors spherical symmetry locally, right?
Exactly. Yeah. That's what you see in the small scales here.
So total time is this is some 40, 50 whatever.
This is about 50 million years.
Beautiful.
But by how much did the magnetic field actually increase in the duration of what we see here? It's not very much, probably.
That's not very much. We can wait for the start of the simulation again. Let's see what color it starts. So it's about here. So it's 1. And then the strongest, it's like, maybe 1 or 2 orders of magnitude. So that, there's been simulations by Balzara. This is basically taken from a model of Balzara. And they don't find that much field amplification. They find that the field is also not going to large scales, as you would expect, because there's no mean field dynamo, and that it saturates rather at low values. So you really need a mean field dynamo to create a significant field. This is now the phase space diagram, as you've seen it for TI already. So the TI was basically this region here. Now we extend to much hotter, much more dilute gas here due to the energy input from the supernovae. The supernovae is basically what happens here. It's so fast that you cannot resolve it. We set up something at very high pressure, and then it cools down. And what you can see here, there's a constant pressure region. That's the old remnants. That's the interior inside of the old remnants, while the clumps are found here. And you get this trimodal distribution that McKee and Ostreicher proposed. You get the dense phase, the warm phase, and the hot phase from the explosion. So it's this 3-phase medium that was the model of the 70s.
So why 2 curves on the histograms? So you selected by temperature, or?
This is volume average PDF and the mass
okay, sorry.
Yeah, I should mention that. And this is now the mass fraction. In the other plot it was the volume fraction. And you can see you spend 6 orders of magnitude in the density and maybe 4 orders of magnitude in the pressure. So this is really a high dynamic range, and you need to put some effort into simulating that. So here's the vertical structure. This is again density. This is the integrated density, so this would be column density. This is the pressure, temperature, magnetic field strength again. And you again see for the midplane there's a nice correlation between the density and the magnetic field. But away from the midplane, this isn't the case anymore. So if you plot the distribution, the rho versus phi, you can really get a nice correlation in the midplane here, where the amplification is really due to compression. But this is not the effect we're interested in. We really want to look into the effect that comes from the gradient here, the mean field dynamo. So this is one of the main simulations. You can see here the clumps again near the midplane. You can see bubbles forming. You can see how many explosions go off in the hot halo. And if you look at this, this turns from dark green to light green. So you really amplify the magnetic field over several orders of magnitude gradually.
So, you said you have a good correlation between magnetic field and density, right?
Near the midplane.
Near the mid, but on the arms of the galaxies we see exactly the opposite, right?
Yeah, that's the mean fields. I'm talking about the small scale field.
Okay.
That's correct. Yes. So
the boundary condition at the top and bottom.
It's outflow and again perfect conductor for the magnetic.
So you lose mass.
Yes, but not a lot because I go up to 2.1 kiloparsecs here. So the simulations of Marit were up to 1 kiloparsec. Actually, here you have quite a bit of mass flow. So you lost quite a bit of mass in your simulations, but it gets because the density profile, the mean density profile stays quite constant. You actually lose very little mass up here. It's only a few percent over several hundred million years. So I didn't need to refeed any mass or anything.
But the field is kind of filling everywhere, although the density is not. Is that right?
Yeah, you see that it's very narrow here. The strong field is really confined to the midplane. I get very like 90 parsec maybe scale height. The field is really in the midplane.
But the white regions right at the top of the box.
Yes.
Oh yeah, there's always. I mean, if shocks collide, then you locally get an enhancement of field, but that's not a mean field. You would now have to take a box average to see the evolution of
magnetic field scales with rho v squared, and rho grows upwards. So the scale height of pressure is much larger than the scale height of density.
Rho falls down.
Rho falls down, v grows up. So the velocity grows up.
Okay, but now we want to not only look at movies. Oh yeah, there's one thing that's a galactic fountain. If you plot the vertical velocity as a function of the density, you really see that this distribution is skewed. So at high densities you have a downward motion, while at low densities you have an upward motion. So you really have warm material being expelled to the halo, cooling down, condensing into clumps, and then see these clumps raining down. You can actually see that in the movie. If there's a shock colliding and forming a clump here, this clump then falls down and it creates a sort of head-tail configuration as it's observed in high-velocity clouds. So it's actually already quite a bit of physics going into these models and already quite a bit of stuff you can take out there. So now about magnetic field amplification. After all, this is a school on dynamos, not an interstellar matter. So these are the first simulations that actually find an exponentially growing field, and it's growing on timescales of several 100 million years, which is faster than expected from the old mean field dynamo models. It has quite high radial pitch angles, although that goes away again if you go into saturation. So this has to be checked because the real galaxies are obvious in equipartition fields. When we observe, if you vary the supernova rate, and look at the ratio of, that's also from observations you can find a ratio of the fluctuating field to the mean fields, and we find that this is about a factor of 5 or something, so the turbulent field really dominates. This is also something that is not met by the cosmic ray simulations of Michael Hanasch, where the turbulent field and the mean field are of the same size. So this is really a turbulent setting where the turbulent magnetic field also dominates. And we find if we vary the supernova rate in different simulations, we find that the regularity of the field scales with the star formation rate, which is a recent observational result by Christoph Shishi. As a side, we find no dynamo for the case of rigid rotation. We are slightly subcritical for an alpha, for an omega squared, alpha squared dynamo. which I figured is related to the dominant vertical transport. So there might be a point in parameter space where also alpha squared dynamo might work for galaxies that are more irregular, that don't have a strong differential rotation, but that has to be checked. And we also find no dynamo for Cartesian shear, so we really need the Coriolis forces to introduce the vorticity.
What do you mean? Cartesian shear?
Just shear without Coriolis forces. So this
no rotation, you mean?
And
yes.
On the next slide I'll show what I believe is the reason for that. Maybe let's skip this.
Yeah. Shear it's supposed to represent the local Milky Way neighborhood.
This shear rate is 1, so it's omega going as 1 over r. So that's
right, but your box is not at the center of the disk or whatever.
No, it's at the position of the sun. So we took the parameters of the copy model, but what we did is we increased the rotation rate. So here the labeling F is full, Q is quarter, H is half supernova rate. So the letters give the supernova rate, and the numbers give the rotation rate in units of 25 kilometers per second per kiloparsec, which is the solar value.
Oliver, when you plot B squared average, right? You put together fluctuation magnetic fields and the mean magnetic fields.
No,
right?
this is the mean field on the left. I should have mentioned it. The mean field and the fluctuating field on the right. Okay. So these are the two, and you can see that this is higher. So you see, if you look at the Q4, H4 and F4, that's different supernova rates. That's the red lines. They all basically the same. So it only depends weakly on the supernova rate. And if you look at the F to the full, the F1 is the only one that is a decaying field. This is the simulation that Marit, Corby, and you guys did. And if you double this, you can already excite a dynamo, and it grows much faster if you go to 4 times or 8 times the rotation rate. Although you already find a growing fluctuating field in this case, just no, the mean field effect isn't there yet. Here's the growth rate of the magnetic field as a function of the supernova rate. So this is the galactic value. And you can see that you can go down to 0.1, the galactic value, and you still reach the same growth rate. So the effect is more or less saturated with respect to the driving. And this means that this works probably equally well in a starburst galaxy or in a very old galaxy with little star formation. So this is a very robust mechanism, really. This is to look at the effect of rotation. So this is without rotation, without Coriolis forces, you don't get a dynamo. And I also checked whether the thermal instability makes a difference, and it makes a bit of a difference. Actually, the field grows faster in the absence of thermal instability. And I think I tried to explain this in my thesis, but I forgot what the argumentation was. So it was a bit counterintuitive, and was also not quite obvious why that would be. Kamna raised the question of the fast dynamo, and what I did to check this, I write the magnetic Reynolds number. This 20,000, 10,000 has to be taken with a grain of salt. That's probably not fully resolved on the numerical grid. But what we see is a trend to higher growth rates for higher Reynolds numbers. So this is really a fast dynamo. It doesn't require microscopic diffusivity for reconnection. It's really turbulent reconnection. The idea is that as soon as you have a turbulent cascade, you have an inertial range where only your nonlinear terms are relevant, which means that whatever happens here on the large scales doesn't depend on the small scales. So you're not, the microscopic eta is not relevant for your physics, because your physics happen at the large scales, and you're detached from the dissipation scales by a turbulent cascade. And I think that's what you see here. You really, the growth rate even increases with increasing Reynolds number. And this is really the hallmark of a fast dynamo. And this is not the case for the cosmic ray dynamo, where the effect goes away if you set your numerical, if you set your explicit diffusivity to 0. This is
have you shown that, or how do you know that?
I think that's a result of their publications, that if they do only numerical diffusivity, then they don't have field amplification.
I think they have closed boundary conditions at the top, right? If I remember correctly. There was something with boundary conditions.
Okay.
On the top, you mean?
Yeah. They're open on the top.
They are open.
They're open at the top.
The same configuration like
Okay. So at some point I really want to also include cosmic rays into the model here with the kinetic driving to really see if there's an additional effect or... So how do we...
Sorry, just a comment that fast magnetic reconnection doesn't solve the helicity problem, because you still get reflection of the microscopic ether because of the helicity conservation. I mean, the helicity is conserved even when there is reconnection. So those things, that's the leap, and that's also in a few experiments one finds.
I think in these simulations you actually can get rid of the small scale helicity by blowing it away.
It works differently. I'm just saying as a comment, in a general matter of principle comment. Even if you have turbulence and reconnection, you have no sensitivity
so you can
no sensitivity for the energy dissipation and energy transfer to the microscopic ether. You still need to solve the helicity problem. You have solved it somehow, that's right. You're getting a growth still.
And I wanted to close the lids, but it crashes, unfortunately. That would be a check if you can...
Yeah.
I mean, Hando is talking about the nonlinear saturation. At this point, we don't really see the saturation phase very well yet.
No, that thing is that as soon as the magnetic pressure, you can already see that the mean field rises, the B phi rises while the BR sort of gets flatter. So this looks like we're losing the pitch angle, and it's only the nonlinear, the linear winding of the B phi there in the end. But the model falls apart because the disk floats up by the magnetic pressure, and then the prescription of the supernova driving isn't quite consistent anymore. So we need new simulations to really look into the saturation. But what I see is that there's a current helicity building up, and this is quenching the alpha. So it seems that it's really dynamically quenched. But that's something that one would have to look into at better results simulations with a different prescription for the supernova distribution.
But however, this magnetic field of 10 to the minus 1 microgauss, it cannot be dynamically so important as to destroy the disk or something. Right? If it was 10 microgauss, 100 times stronger or 10 times stronger.
I mean, the RMS field is already pretty close to microgauss.
It still means dynamically subdominant. But obviously it's a complicated problem. More work needs to be done.
Oh yeah, but that's definitely one thing that is
the
very interesting, the quenching of
very
the
interesting question.
and whether you can retain the pitch angle in the quenched state. Yeah, I also wanted to close the boundaries, but that crashes unfortunately, to see whether you can switch off the dynamo by retaining the small scale helicity. So let's try and understand what we see in terms of dynamo coefficients. So I measured the alpha eta profiles with the test field method, and this is always as a function of the vertical position Z. You get a positive effect in the northern hemisphere and a negative in the lower, and this matches with the SOCA prediction quite nicely. You get the desired amplitude. What we find is that the diamagnetic pumping is directed inward, unlike predicted from these bubble models by Ferriere, who predicted a positive gamma, so we find a negative gamma.
But that's because the turbulent RMS velocity is increasing outwards.
Yes, exactly.
Which is very natural.
Although in the alpha effect, it turns out it's actually the gradient in the density that makes a dominant effect, not the gradient in the U dash.
And then it's different. That has the opposite sign.
Did I just mix it up? I would have to, but there was one of the two dominating.
Yeah, right. I think
Homogeneous gradient of V square.
Or actually,
yeah, but here's
Rho
actually
isn't involved, right?
that's what I thought. But you have in your formula a rho.
there's also the u dash squared. It's actually, you can see it here near the midplane. You also get a negative effect. This is due to the density gradient, which is strongest in the small disk with 90 parsec. So this is really this 1 kiloparsec. So 90 parsec would be here. This is the density gradient, and this is then the velocity u dash gradient that makes the positive effect. What you can see here is that the gamma is about a factor of 2 larger than the alpha as predicted by Soka theory, and that is not prohibitive for your dynamo. On the contrary, it's really that this pumping, this inward pumping, is balanced by a contribution from a mean flow. So we have a mean flow that drives the field away, and this is balanced by inward pumping, and these are really same order of magnitude. And I think we can argue hand-wavingly that this is a result of energy equipartition between the kinetic pressure and the gravity and the thermal pressure. If you plot the potentials on top of each other, they nicely add up. Yeah, I think I've mentioned all of these. So the test field method that Axel informed me about 2006 at the Think Shop in Potsdam was really beneficial in measuring these. I used these fitting methods before, and it was just a big mess. And you just have noise and negative ethers, and here the ether is really nicely positive. It really nicely follows the shape of the u dash squared as predicted by Soka, where you can estimate your turbulent diffusion by the turbulent velocity. So that's what I use to estimate the coherence time of the turbulence, which is rather low compared to what's usually assumed. People assume the high values to get their alpha big enough.
Well, if you calculate this coherence time as a time between the passage of the shock wave through a given position, you get exactly this number.
Oh, okay. That I didn't know. People usually use 10, 20 mega years.
You know, this is the edit nova time. But if you estimate, you made this estimate, I think, in the book with Rosmark in 1988. This estimate is there. So if you estimate the time separation between the passages of the shock wave during the supernova through a given position,
okay,
you get this sort of.
If I take the size of these, the correlation length from autocorrelation functions or structure functions, I get 100 parsec as a typical length scale, which shouldn't be confused with the size of these bubbles because it's really turbulent thing. But if I compute the Screw-Hall numbers afterwards, they are order unity, and that confirms that the Soka estimates are order of magnitude correct. Because that's the sufficient condition for pulling out the integral. And then I also found, Günther never believed me that this is significantly positive. What's your take on this? This is I find a significant positive contribution to this delta effect, to the omega cross J. And if you add the negative shear, you can actually drive a dynamo with that. And I did some mean field results on this. And it slightly affects the parity of the final result.
So it's 0.5 plus minus what?
Yeah, it's roughly 0. Yeah, I wouldn't want to give error bars on this, but it's an effect, and it has some magnitude that's on the order of the turbulent diffusivity. So you might get a supercritical excitation if you shear or rotate fast enough.
Many of these things seem to peak at about 1 kiloparsec rather than in the disk, isn't it? The alpha which you had in the earlier plot, if you just go back to the earlier.
Yeah, that's the thickness of the. You get an M-shaped profile for the turbulent velocity as well. So you go up to 60 kilometers per second, I believe, and this is like 20. So you get this M-shaped profile, which is a consequence of the momentum conservation in the vertical direction. So this and this depends on the strength of the gravity and on the supernova rate, but only weakly so. That's why the effect saturates quite early.
Yeah, what I meant was, you see, normally when we are doing these simple mean field models, which Anwar has discussed, you would assume a disk of, say, a height of some 500 parsecs or 400 parsecs or something, right? And you think of an alpha effect in this. But in these simulations, we seem to be getting the alpha peaking at 1 kiloparsec rather than anything else. So the thickness of the disk is really, one needs to take it to be much bigger in this sense, which is, of course, a good thing for the dynamo.
Because you have it in the dynamo number.
Right, but on the other hand, it's not so good for the time scale. On the other hand, you seem to get a shorter time scale. These things all have to be thought about, yeah.
But yeah, that's what I meant with a foundation. You really have a measurement now. You don't have to assume something or estimate something. So
the station is not clear here. The scale height of 500 parsecs is for the sort of mixed neutral and ionized gas. But 1 kiloparsec is the scale height of the distribution of free electrons, for example. So it's not clear how all these things are related. So this is interesting. It doesn't mean the difference in these behaviors. It can be an artifact, or perhaps not.
Yeah, anyway. It's just that I noticed it now.
Definition of eta, was it eta 1, 2 minus 2, 1?
Here, I have a minus sign in the phi r.
Yes,
here
fine.
to make it also positive.
Yeah. I think then the sign is expected as from SOCA,
Is it
which is positive. It's the same direction as omega in this definition. And that's what we had in the 2008 paper with Karl-Heinz.
in what case of force turbulence?
Force turbulence. It's just rotating. When the eta t was how big again?
Yeah, 2
Oh, 2.
kilopascals.
But why it's 0 at the midplane? It should be maximum at the midplane, or not?
The eta?
Yeah.
No,
No.
that's because the density is high and then the turbulent velocity is low if you have a momentum balance. The U dash profiles really go really down here.
But not 0.
It's not quite 0, but it's it's actually here in this plot. It's really low. That's,
The units are like that.
The units is...
Because the tau is small, it's 3 into 10 to the 6 here, rather than 10 to the 7 that you normally would have thought.
The standard estimate is 1.
Yeah.
maybe we discuss that later on because I'm already running over time. As I said, we didn't find a dynamo in the case of shear alone. And here I plotted again the alpha effect, which is positive for differential rotation, and this is really dominated by the rotation in this case. While when I switch off the Coriolis forces, I get a negative effect, and you sort of can understand that if you look at this profile, the shear counteracts the overall direction of rotation. No, actually, there's the overall direction of rotation is of course this way, but the Coriolis force has a minus sign. So your remnants actually get swirled in the opposite direction. And if you then look at the effect of the shear, they tend to distort the remnant in the opposite direction. So you would expect in the case of shear, because the Q is negative, you would expect a negative alpha effect here.
But you don't get zero, and that's interesting.
What do you mean? If you have both?
No, if you have just shear without rotation, you don't get a zero alpha effect.
No, because I have stratification, and there's a
yeah, you have negative vorticity.
Yeah, what is it?
There's a paper by Günther and Leonid 2006 where they actually do this as a response to the Yusuf and Alberg, I think, and show that there is no, and you need stratification, of course.
Yeah,
in this case,
right.
It's really a classical cyclone.
Yeah, Karl-Heinz also had it, and we confirmed it with Petri.
Yeah, what is the scale of your magnetic field in Z direction? The question is about the the ratio of alpha effect and omega cos J effect. Your alpha is a few kilometers per second. Your delta is 4.5 kilo per second, kilometer per second. And if you now say, okay, I have scales of 1 kilo per second or so, and I would say, okay, alpha effect and omega cos J effect are comparable to each other. Is it true or?
That's a good question. I've never did it in a quantitative fashion. I could run a mean field model with the alpha amplitude from the simulation, and then one with just the delta effect, and compare the growth rates. I've never done that actually. The scale of the magnetic field it's rather narrow. It's about 140 parsec scale height. So the mean field is really strongly peaked. So if you would consider that for a length scale.
If the scale is small, then it would be good for the
omega cos J.
Omega cos J. Okay. Thank you.
Okay, so in these cases we have the opposite signs, and as I showed earlier, this means different directions of propagation of the dynamo waves. And this is now a small parameter study where I looked in the growth rate of a mean field model as a function of the pumping. This is inward pumping, strong inward pumping. This is node pumping. And these different lines correspond to different advection velocities. And you see in the case of differential rotation, for moderate inward pumping of like 5 kilometers per second, we get a growing dynamo solution with a growth rate that's about consistent with simulations. In the case of shear, the inward pumping you need to counteract the outward vibration of the dynamo patterns is much higher. So you need a lot more inward pumping to get a growing dynamo solution. And around the values that we have in the simulations, like 6 or 8, you see that there's actually only a marginally excited dynamo. So this can explain why we don't see a dynamo in the case of Cartesian rotation. And as a last slide, this is called the saving computer power. The left-hand side is a butterfly diagram from the simulations. This is 1.6 gigayears. This ran on 128 CPUs for like 3 months, applying a direct simulation in the VR and the P5. We get a quadrupolar parity, and we get, after 1 gigayear, we get a field reversal, which has this characteristic lopsidedness. And we could reproduce this by taking the alpha and eta and plugging these into a simple 1D toy model. And these simulations, they ran 2 seconds on my notebook. So this is a factor of 10 to the 9 in computing power. That you can now measure these alphas, and then you can of course do 3D mean field simulations, because all this change of parity and everything that might depend on a local approximation that might be different if you go to this configuration. But you can now measure the alphas as a function of supernova rate, rotation rate, plug that into a global mean field model and see if you can reproduce spiral arms and everything. As a note, this lopsidedness of these reversals, that the field is stronger on one side, that's something that is an effect of the delta. So if I don't do the delta, the thing is perfectly quadrupolar, and if I include the contribution from the delta effect, I get this characteristic lopsidedness. So you need, as Matthias Reinhardt mentioned yesterday, you need really all the tensor coefficients to reproduce your simulation, and they are all significant.
So say again.
Predict a reversal of galactic fields.
Yeah, that's Rainer Beck, and there's a paper by Fritz Krause and Rainer Beck that there seems to be a predominant inward pointing field in that example.
One outward thing or something, yes.
But if you really have a field reversal, that might not be significant. But as I said, this might be an artifact of the local approximation. So I think Detlef has found that if you take these alphas in global simulations, you don't get the reversals. But this was really to check the applicability of the mean field approach. And as you see, you do a rather nice job in reproducing characteristic features here. So I'll just leave you with the conclusions and thank you for the attention.
Thank you. Some questions, please. So that was green computing, as you have seen here.
Yeah.
Green computing, because we save computing power.
Oh, yeah.
Can reduce CO2 emissions that way.
I don't want to think about my CO2 footprint. Running simulations on 500 nodes now.
But maybe one should really think of this the other way around, because the computing of galaxies in the computer is already quite expensive, but we can never go to the real astrophysics, of course. And so we have therefore a tool which we have now gauged with by finding agreement with the simulations. We have now a tool with which we can go far beyond. So that's, I think, how I would like to see that. Further questions?
All interruptions during the talk.
Yeah.
All possible.
The question is, how long does one have to run before you see the saturation effects? Now I understand that you probably have not yet hit the helicity problem at all. And it's basically because your mean field has not grown yet.
To saturation and beyond. I mean, when
Yes.
we often
So
see that
although the galaxy will hit 10 billion years, or galaxy will hit.
I mean,
So you may have to, but your thing is growing very fast in 100 million year time scale, exponentially. And therefore I would imagine that even if you went to one more giga year, you should start seeing the effects of, you grow by factor of,
But I mean, I see a turbulent field that already approaches microgauss.
Yes, but we want to know what the mean field does. Because we see the mean field, which is several micrograms or whatever it is.
But even if I take a conservative, I mean, the Reynolds number I define is basically this velocity times this size over L omega squared over V omega squared over this L. So the 10,000 is probably too high, but even if I take a conservative estimate on this and say maybe I have a factor of 100 dynamic range and take this at my Reynolds number, then I would assume that the quenching takes place at like 10 to minus 2 microgauss, right? Or maybe 10 to minus 1 microgauss.
What quenching?
The catastrophic quenching. If that should really be the case, then I shouldn't get.
Oh yeah, I mean, we don't think that there would be this catastrophic quenching until you cancel the alpha by your current helicity, which you are producing in this box. Correct. So it will carry on, I agree. It will not, because the catastrophic quenching is an assumption, is a result of various assumptions that finally put in, like stationary state for the helicity, and then you get the catastrophic quenching formula. So it's not something which you should blindly use as such. So this thing will rise, I expect. But will now saturate once your alpha magnetic has grown sufficiently, I think. So it will be interesting to see what happens at that stage. Whether it will still
unfortunately where the model falls apart. So.
Yeah.
Do you understand this, by the way? Why is that? Is that a serious problem, you think, or why is it actually?
I really think it's magnetic pressure becoming important and then spreading out the disk, and then my prescription of that the supernova distribution in the vertical direction follows the density profile leads to a broader supernova distribution. You really see how the supernova distribution spreads, and that leads to a further spreading out of the disk. So I basically disperse the disk.
But as Anwar says, the magnetic pressure is not. Some number is missing because the magnetic pressure is not so high. So somehow you lost all your cold stuff in the center of the disk, is it?
That's correct, yeah. I maybe we can look into that and look how large the magnetic pressure really is in this case. But you see the disk dispersed, so the model has to be refined too. I must say there was already a bit of fiddling going into this. If I just take a static supernova distribution that will lead to as soon as the disk midplane gets a bit off center, it will be driven away, so you get an undulation of the whole disk, and then you can damp it critically with the gravitational force, so you can compute the damping constant to be critically damped. And then that would keep the disk in the midplane, but then that would split up the disk into two. And so that's when I decided to make the supernova distribution according to the mass density, and then that solved that, and it got into a stationary state. So this,
please, yeah.
How important is to have a mesh refinement in simulation of turbulence? Is really something that you need?
There's different opinions on it. Some people say turbulence is space filling. If it's a low Mach number, then you don't gain anything by mesh refinement. There's the opposite idea that if you go to high Mach numbers, you're dominated by shocks, and then you can actually gain a lot by mesh refinement. And there's a group in Würzburg, they are doing the fearless project. They are combining mesh refinement with subgrid scale models, and that seems quite promising. And they can measure the fractal dimension of their intermittent structure by the mesh refinement hierarchy. That's like a box counting dimension. And so there's actually use for that. I must say I implemented the supernova model in mesh refinement, so it was not so easy because you have to know where a supernova goes off. So you make a list with pending supernova events, and then you have to tell the code to refine at that position, and then when the mesh refinement is reached in a shell there, then you can put in the energy and get the explosion.
So for the mesh refinement, you have a monitoring function? Like you check
There's refinement criteria based on density gradients, on second order derivatives of. I think in this case I used density gradients, yes. And the problem is with the supernova turbulence, the point where you actually gain something by the mesh refinement is not quite clear. And Miguel de Aviles did up to 10 kiloparsec, and then of course you gain something with the mesh refinement, but then there's not so much interesting stuff happening there. So, and it's difficult to implement these shearing boundary conditions with mesh refinement, so that hasn't been done yet. So all these simulations are without mesh refinement.
So that was very exciting. It was great to hear your latest accomplishments of this code. Thank you very much.